fair, all right? No puzzles were involved in the questions. And as a matter of fact, some of you guys could even get 120 points, right? There was, I guess, 20 points of bonus question. So I expect rather higher grades, but only today I could receive your exam papers, so I didn't have any time to even start evaluating them. The evaluation will take some time, and I will inform you about when the evaluation may finish. And those of you who are curious about the grades he or she may get, you may come and see your papers. You will be able to come and see your papers before I submit. So since the questions were not tricky, okay, there were no tricks involved in the questions. They were just plain calculations and knowledge questions, except for the bonus question. But even that one was not too difficult, because it just requires the fact that multiplication of two odd signals, two odd time signals, will make an even signal, and multiplication of an odd and an even signal will make an odd signal, and symmetric integration of an odd signal will give you 0. Okay, those are the only things that you are required to know to answer that question. So let's get rid of that first midterm. We can come back to that concept if your grades might be disappointing, but I didn't start evaluating them yet. So we may return to the exam issue later. Today we will continue with our discussion. If you don't have any further questions, if you have some specific questions regarding some question inside the exam or something like that, please ask me. We may talk about that. If most of you are confused about a question or something, then we may talk about that. So the thing that we were discussing was the Fourier series coefficients. There were some questions regarding the Fourier series coefficients in the examination, but those questions did not involve any calculation of the Fourier series coefficients using the formula. What was that formula? Let's remember in continuous time. So our topic was continuous time Fourier series. This was the topic, and we have already said that for a continuous time periodic signal, x of t, any periodic signal, it can be represented in terms of infinite summation of scaled complex exponentials. And the complex exponentials have a frequency of an integer multiplied by a fundamental frequency. And this fundamental frequency, omega 0, we could also write it like this, if you wish. K from minus infinity to infinity, ak e to the jk 2 pi over f0 t. So omega 0, the fundamental frequency, 2 pi f0, sorry. So this is, either we have to write it as 2 pi f0 or 2 pi over t0, sorry about that. That t0 is the fundamental period. So f0 is equal to 1 over t0, or omega 0 is equal to 2 pi over t0. This t0 is the fundamental period of this periodic sequence. That is quite interesting because we're not combining arbitrary complex exponentials. These complex exponentials, which are sinusoids, these sinusoids have frequencies in integer multiples of a fundamental frequency, which is f0 or the corresponding omega 0, like this. So we don't have, for example, an arbitrary frequency here, which is omega. It must be an integer multiple of a fundamental frequency. That's why we are considering only periodic signals. The period is t0 and the frequency is omega 0. But the harmonics, there are harmonics about this. It's not a pure sinusoid that we have. If you have only one pure sinusoid, then this summation will consist of only a single term. It won't be a summation anymore. It will be a1 e to the j 1 times omega 0 t, which has a frequency of omega 0. That's it. But there are other harmonics, and all harmonics are at integer multiples of the original frequency. That's the flavor of the Fourier series representation. And the Fourier series representation requires the determination of these so-called Fourier series coefficients, AKs. And the formula we have derived before, but I didn't ask anything about either the derivation or anything that requires that formula. And the formula was something like that. We were multiplying both sides of the equation with another complex exponential. And then we were integrating both sides and make the simplifications and isolate this AK term from that equation. If you rewind and watch the video regarding that, you will see how we derive this. And the derivation, after the derivation, the formula we obtain is like this. This is T0, the period. And I'm going to write under the integration term T0, the same period. It means that the starting point of the integration doesn't matter, but the length of the integration is T0. It may be, for example, from minus T0 over 2 to T0 over 2. It may be from 0 to T0. Anywhere, okay? Just shifted versions, but the duration of the integral is always T0. That's the necessary condition, and it always gives you the same thing anyway. X of t, which is our periodic signal. So you integrate over one period, and you don't care where you start and where you end. It must only occupy one period anyway. E to the minus jk omega 0 t dt. So this is a formula that we obtain. And we need to use it. And this omega 0 is the same omega 0 as the above thing, which is the fundamental frequency. And as you see, the index of the Fourier series coefficient, the kth Fourier series coefficient, depends on k times omega 0, which is the kth harmonic. That's how we evaluate this term, the Fourier series coefficient. This Fourier series coefficient has this general form, and we will start seeing examples about that, and soon we will come up with some properties about easily obtaining these AKs from any given periodic shape. We usually need one period of a periodic waveform because the integration is inside one period only, as you see. And these will describe the magnitudes or the scaling factor of any harmonic that the periodic waveform contains. If you have already seen power electronics related topics, they say that, for example, the voltage waveform has harmonics. That's a bad thing. Or if you haven't seen it yet, you will see in future lectures regarding power electronics and things like that. They say that the voltage waveform has harmonics, which is something bad. It means that the voltage waveform is not pure 50 hertz sinusoid like this, a pure sine wave. It may be, for example, a square waveform or a sinusoid with some ripples like this. These two waveforms have harmonics, and that is a bad thing because the electrical machinery, the analog equipments, in terms of the electromagnetic rotation mechanism, requires us to have sinusoids. Because only a sinusoid is a reflection or a projection of a rotary motion. These things do not correspond to a pure rotation in terms of the flux of the motor or the electrical machine, for example. So they don't want this one. They don't want this one either. They say that they contain harmonics. But what does it mean? It means that this sinusoid is containing a few more, maybe infinitely more, Fourier series coefficients that are not zero. Normally, we should only have one non-zero Fourier series coefficient for a pure sinusoid. But these two guys have more than that. That's why they call it, they contain harmonics. And one other thing that you have to be careful about is that this AK could be, and in general it is, or they are, complex. Okay, they are not real values. They don't need to be real values. They are complex values, and a complex value here correspond to you, or as an idea you may think of it like that. If there is something complex here, then it means it's a magnitude and an exponential in the angle term, e to the j theta, like this. A complex AK is the magnitude of AK, e to the j theta. Theta is the angle. This is a general form of a complex number. Such a complex number pushes this theta into the complex exponential, making a phase. So that's how we have we can have any kind of a periodic signal as a combination of harmonics, and those harmonics, those sinusoids, may correspond to sine waves at different phases, different amount of shifts. Those shifts are governed or handled by complex AK values. Now, we can start by seeing examples of evaluating AKs, because at the end, whatever that may correspond to, I'm trying to explain you what it means, what they mean, the AK Fourier series coefficients. But whatever they are, you have to find them. Eventually, in order to solve questions, you have to develop the necessary skills to give an answer to what are AKs. For example, if x of t is described like this in a single period, it is, so let me put x sub 1 of t is 1 when t is less than capital T1, and 0 when it is greater than T1 in magnitude, and less than the period over 2, half the period. This looks a little bit awkward, but this is only within a period. And when we draw it, it means this. This is minus t over 2. This is t over 2, let's assume. And this goes on, because it's infinite extent periodic signal. From minus T1 to plus T1, it is 1. And it is 0 from T1 to T over 2, or from minus T over 2 to minus T1. So these are the 0 portions. This is the portion with a magnitude of 1. But it's only valid within one period, and you have to extend or replicate it with a period of capital T. Half of it is T over 2, so the normal T value is here, and we have one more component here. Then we have, how far away is that? Somewhere here. Around 2T, we have something like this, and it goes on. Minus T, for example, etc. So it is periodically repeating itself as a rectangular pulse, and it is periodic. Therefore, technically, we are expected to find the Fourier series coefficients for that. And how are we going to do that? The best way to start with is the determination of A0, which is the DC coefficient, because when k is equal to 0, let's come back to this formula here. This formula, AK. When k is equal to 0, we're going to find A0, and A0 is 1 over T0 x of t e to the 0, because k is 0. e to the 0 is 1. So that is the integral of x of t inside one period divided by the period. What is that? It's the average value, the DC value. So this A0 corresponds to the DC level. It is not a harmonic. It's a harmonic corresponding to frequency 0, which is a constant. So that is this integral. So this is x1 of t, and x of t is the periodically extended version. It makes sense to take the integral limits from minus t over 2 to t over 2. Some students who may not be very experienced may attack the problem like this. They may take the integral from 0 to t. That's valid. There's no problem about that. There is a problem, but it's still okay. What's that problem? If you do it that way, there is this much 1 level, and then some amount of 0 level, and then some amount of 1 level up to t. So it requires some extra effort. Don't do that. Please take a look at your waveform and choose the best integration limits of one period. I have chosen from minus t over 2 to t over 2. This region I have chosen. It makes more sense because inside that there is a continuous or persistent level from minus t1 to t1. In fact, I can rewrite this thing as 1 over t from minus t1 to t1 of x of t dt, because all the others from minus t over 2 to minus t1 and t1 to t over 2, they are all zeros anyway. They don't contribute to the integration. And within this interval, the value of x of t is nothing but 1. And this integral will give you 1 over t of 2t1 or 2t1 over t. This is the DC value. And it makes sense anyway because the width of this thing is 2t1 and it is once within this duration. But it must be normalized with the period of everything, and the period is capital T. So 2t1 of them is 1, and the average is 2t1 over capital T as a DC value. Of course, this is the easy part. The other components will require this formula with individual or separate substitutions of k. We must find for k is equal to 1, k is equal to 2, k is equal to minus 3, k is equal to minus 4, everything. Of course, we will generalize this. So what's NAK? Let's rewrite this formula, 1 over t. Integral, again from minus t over 2 to t over 2, the same limits. But since I'm integrating x of t times something, that x of t is non-zero only from minus t1 to t1. So do you agree that it makes sense when I write the integral limits like this? Outside this integral limits, it is all zeros anyway. So within this limit, x of t is 1. And then we have e to the jk omega 0 t with a minus and dt. So this is the integral that we are looking for various values of k, except k is equal to 0. That is already found over there. So what is this? Sorry? Oh yeah, of course. Yeah, this must be from minus t1 to t1. I just forgot to put a minus sign over there. So this is the integral that we need to evaluate and generalize for any given k, and that is an exponential integral. The integral of an exponent is 1 over that exponent term, that is minus j k omega 0, right? And then there is 1 over t, so let me put this t also here. And then we have the same exponential term, e to the minus jk omega 0 t from minus t1 to t1. It's an easy integral for an exponential function. And we need to evaluate that. You just need to substitute t1 here first, and then subtract from that the substitution term of minus t1. And what will it make? It will make 1 over k omega 0 t e to the jk omega 0 t1 minus e to the minus jk omega 0 t1 over j. Now this j was previously here. I'm sorry that I'm eliminating or skipping a lot of steps here. I'm not going step by step. I make the necessary adjustments already. For example, this j was originally here and it has been pushed here. This one was with a plus sign, this one was with a minus sign. But there was already a minus sign here, so I got rid of that minus sign and replaced their orders like this. And furthermore, I'm going to do one more thing now. I'm going to put a 2 here and another 2 here in the numerator and denominator, because once this is being isolated like this, the right hand side is in a form that we should be very familiar with. It's the sinusoid. Yeah, it's the pure sine. So it is 2 times sine k omega 0 t1 divided by k omega 0 capital T. And that's it. Almost. If you further simplify, even this one is suitable for further simplification, because omega 0 is equal to 2 pi over capital T. So when you multiply both sides with the capital T, this is omega 0 times capital T, these T's will cancel and you will have 2 pi. So this multiplication is nothing but 2 pi. And there is a 2 here already. So the further simplified form is sine k omega 0 capital T1 divided by k pi. So that's it. When you write it and encircle it like this and say that these are AKs, you will get full credits, 10 points. If you give me something like this, you will get 10 points. If you give me something like this, I'm not sure. Maybe 9.5, but still close to 10 points, because that's the answer anyway. It doesn't really matter whether you make the eventual simplifications to come up with such a desired formula like this one. But it's possible, of course. So this is how you find the Fourier series coefficients. If your signal, if your x of t is consisting of such flat shapes like this one, then it is possible for the student to take these integrals. They are manageable. But as you may guess, if the shapes here become complicated, it may become more and more difficult to evaluate that integral with some shape formula here. Instead of 1, there will be some shape formulas. For example, ramp signals, triangular waveforms. By the way, even the triangular waveforms are too easy to integrate. But they are not as easy as this one, of course. So we have to do something else for those arbitrary signals. For those arbitrary signals, by the way, we will use some properties. Usually, knowing this thing only is more or less enough to solve any kind of reasonable question. We will use then properties. We will change this the function shape, and we will know when you change the shape over there, how will this change? This will be changing with a formula related with the shape of the original signal. Of course, we need to learn the association, the formulas about how they change. We will see that. Now, let's come back to this original problem here and make some cool assumptions, like I'm going to write it here. T1 is equal to T over 4 case. That's the following example of the same question. So what does that mean? If T1 is equal to T over 4, it means this point is the halfway between 0 and T1 and T over 2. What does that mean? It corresponds to a half duty cycle, periodic rectangular waveform. Half of the time it is ones, half of the time it is zeros. Half of the time it is ones. And it goes on like this. That's a special case corresponding to a half duty cycle. And that half duty cycle is a commonly encountered situation. And over there, the same formula for this AK becomes, let me rewrite it, sine k omega 0 T1 divided by k pi. But T1 is equal to T over 4. And then it will make sine k 2 pi over 4, which is pi over 2. Over k times pi. Now this thing is not exhibiting a reasonable value for every k. For example, when k, oh by the way, did you notice why we evaluated A0 separately? I have forgotten to mention about that, because this is the general formula, and you could say that without dedicated analysis of A0, you can tell me that this is AK including for k is equal to 0. Isn't it? It is. But there is a problem, because k is in the denominator, and when k is equal to 0, you need to evaluate this fraction. Can you evaluate this fraction for k is equal to 0? Yeah, yes, you can. Because the denominator is 0, but the numerator is 0 as well. It's an ambiguous fraction. Sine of 0 over 0. And do you remember from high school or something like that, the Hospital's rule? You have to apply the Hospital's rule here. You have to take the derivative of the top and the bottom separately and evaluate at k is equal to 0, the fraction. The derivative of the top, the derivative of the bottom. And you have to take the derivative of this sign. You have to take the derivative of this denominator with respect to the k parameter here. There is no time. It's k. And the denominator's derivative will be pi. The numerator's derivative will have omega 0 times t1 times cosine 0. And cosine 0 is 1. So it will be omega 0 times t1 over pi. And that is nothing but this, 2 times t1 over t. So it will give you the same thing still. But as you see here, things became a bit more difficult if you don't consider k is equal to 0 case separately. That's why we solved that problem before solving all the other case. Because there's a possibility that k becomes in the denominator, and it may cause a problem like this one. Here, the same problem exists, and for k is equal to 0, still, when you take the derivative of the top, it will give you pi over 2 times cosine 0, which is 1, and the derivative of the bottom is pi, so it will give you 1 over 2. which is in fact correct, right? Because half of the cycle it is ones, half of it is zeros. So what is the average? 1 over 2, half. How about the other case? For example, when k is equal to 1, then a1, which is by the way equal to a minus 1. Why is that? Because this is an odd signal, a sign is an odd signal, but k itself is also an odd signal. For negative it becomes negative, for positive k it becomes positive. So their ratio or their multiplication is even. That's why a1 is equal to a minus 1. It becomes an even sequence like this. It's equal to sine pi over 2 divided by pi. What is sine pi over 2? 1. So the whole thing is 1 over pi. When you evaluate this one, you will notice a pattern here. When k is equal to 2, the numerator becomes pi. And what is the sign of pi? 0. It's 0. It's like this. At 0 it is 0. At pi over 2 it becomes 1. At pi it becomes 0. At 3 pi over 2 it becomes minus 1. And then at 2 pi it becomes 0. So every multiple of pi will make a 0. So this is 0. And so is a4 or a minus 4. In fact, for all even indices, it's a big 0. Okay? So the evenly indexed harmonics do not exist. And for a1 it is 1 over pi. For a3 equals a minus 3, by the way, it is minus 1 over 3 pi, because the top will make a minus 1 and the bottom will make a 3 pi when k is equal to 3. And a5 is equal to a minus 5 is equal will make 1 over 5 pi. And it goes on like this. Can you see the pattern here? a1 makes 1 over pi, a3 makes 1 over 3 pi, a5 makes 1 over 5 pi. So what can you say about the odd indexed terms in general? A 2k plus 1 is equal to what? There is a plus and minus oscillation that we have to handle, but apart from that it is 1 over 2k plus 1 pi, and it is either plus 1 or minus 1. Yeah. Something like that, yeah. It's not k, but k minus 1, I guess. For the first one, it gives you a positive when k is equal to 1. It is not 2k plus 1 or anything, but it must be... Is it k? Okay, that's right. When k is equal to 0, when k is equal to 0, 2k plus 1 is 1. That's where it starts. So it is k, yeah. It's minus 1 to the power k. For k is equal to 2, it will make, when k is equal to 1, it will make 3. For 3, it will be minus. For 5, when this is 5, k is equal to 2, it will be plus. So it goes on like this. This is correct. So it's some formula like this. Now we observe a very nice property of the Fourier series coefficients, another nice property of Fourier series coefficients, which usually exists. And by the way, there is, if you have visited the Java applets page already, it's not only the convolution that exists there. There is also Fourier series coefficient applet. And over there, it displays one by one, displays the Fourier series coefficients. And when you draw any figure, it automatically assumes that it is periodically extended. So it generates a periodic, or assumes a periodic waveform from there, and it plots the magnitudes and the angles because it's complex. By the way, these are real, but it's not in general true. It may be complex. The magnitudes tend to decrease as you increase k. That's a property that you expect from normal waveforms. When k is equal to small, then the value is large. 1 over pi is large. 1 over 2 is even larger than that. So it is decreasing. It tends to decrease. And that decreasing pattern is quite specific. Okay, you must expect something like that. Only for a single type of signal that we will see, it doesn't decrease. It stays the same. But it cannot increase, by the way, by increasing k's. The magnitudes of these coefficients are normally decreasing in time. That is something expected. Again, when you see electrical machinery and such power-related lectures or courses, this will be a very specific example because half-duty cycle rectangular pulse is something that is very undesired. When the power people say that this waveform, this voltage waveform, has harmonics, they usually mean that it contains odd harmonics that are decaying like this, because they obtain such rectangular waveforms, and those rectangular waveforms are usually as a result of like uninterruptible power supplies and things like that. They don't produce sinusoidal waveforms. So this was one example that we have seen. What is the next example? Okay, before seeing the next examples, it may be better to spend the last 10 minutes by writing down some of the rules of the Fourier series existence. Previously I said that if it is periodic signal, then it must have Fourier series coefficients, but I was lying. Because I was only assuming some normal waveforms, okay, that can be drawn with your hands. And then you repeat it, it becomes periodic. But of course, if the signals are abnormal, then their Fourier series, and then we will see that their Fourier transforms also may not exist. The Fourier series coefficients may exist only with these rules. If they satisfy these rules, within a period, its magnitude sum must be finite. So if the signal diverges within a period and repeats itself, what are such functions? For example, the tangent is an example about that, because tangents go to infinity and they are periodic. They from minus infinity to plus infinity they blow, and then from minus infinity to plus infinity again, etc. So they blow and they cannot be integrated. So the Fourier series coefficients of tangent periodic waveform doesn't exist. You don't need to try to evaluate the Fourier series coefficients for such signals. They don't exist. Or you can generate other diverging signals like 1 over t, for example. What's a 1 over t signal? It is something like this. Up to a point, from 0 up to a point, that is 1 over t, and then you repeat it. And you perfectly make it periodic. But this periodic signal is, again, not integrable within a period. Therefore, the Fourier series of such an awkward signal doesn't exist. There are two other equivalent rules or conditions within one period. the number of oscillations must be finite. Again, for a normal signal, it is naturally finite, but consider this strange signal, sine of 1 over t between 0 and 1. And then, since it is between 0 and 1, whatever shape it makes, I'm repeating that pattern and making it periodic. So within one period, it is this. As you see, as time approaches to 0, 1 over t becomes very large, and since it grows indefinitely fast as you approach to t from the positive side, approach to 0 from the positive side, this 1 over t will blow, and sine of that will make abruptly infinitely many oscillations. So the shape, in fact, looks like this. Around 0, there are infinitely many oscillations, and then it relaxes towards, I don't know, 1 or something like that. But around 0, the number of oscillations for this thing is infinity. And that's why such signals must be handled. And then, of course, we repeat it. So we make a periodic signal like this. What are the Fourier series coefficients of such a signal? We don't know. It doesn't exist. They don't exist because it violates the number of oscillations. Similarly, like the number of oscillations, again within one period, the number of discontinuities must be finite. What's a discontinuity? Sorry, I've already erased. Do you remember the rectangular shape that we found the Fourier series coefficients for? This thing. Okay. This is from minus t over 2 to t over 2. How many discontinuities are there? There are two discontinuities. One of them is here, and one of them is here. Two of them. It may be 2, 5, 10, 100, 10,000, 1 million, 1 billion. It is still manageable. You can still find the Fourier series coefficients. But if it is infinity, if there are infinitely many discontinuities, then you cannot find the Fourier series coefficients. Then it doesn't, they don't exist. But such signals, signals like this, are so artificial that you never encounter them. Only a professor can generate such a signal and ask you in the examination. Other than that, you cannot encounter such signals. Let me produce, just artificially produce, such a signal with infinitely many discontinuities from 0 to t. Half of the duty cycle is 1, and then it goes down by half. This is t over 2. And then what? And then the same rule applies. In half of the remaining, it goes that level, and then it goes down to the half of whatever that value is. And then half of the remaining time, it stays, and then it goes down to the half of the remaining whatever, and then it goes the same level and goes down half that level, and it always goes to the half of the remaining. It never reaches to that remaining, by the way. It is always going to the halfway of whatever left. So as you go near and near to that particular point, the number of discontinuities going down half of that value, the number of that jumps will be infinity. So for this artificial signal, for instance, we do not have a Fourier series coefficient resolution. It doesn't exist. This one is still a reasonable thing because sine of 1 over t exists in the nature. It is called the chirp signal, and the chirp signal, the chirp sound is the sound of the bird, right? Because it starts from high frequency and goes down with a high, lower frequency. Or it may be the opposite, low frequency to high frequency. The variation of the frequencies are usually notated as the chirp signals, and scientifically they are valuable signals as well. So this thing is a reasonable situation, but this is quite unreasonable. You have to generate an artificial example like this. These rules about, or the conditions about the existence of the Fourier series was found by Dirichlet, and they are also known as the Dirichlet's conditions. The scientists who discovered these rules, and Dirichlet is the student of Fourier, okay, the PhD student of Fourier. So Fourier found the Fourier series, and his student found the rules of the existence. Technically, you're supposed to first check for a signal. When I ask the question, write down the Fourier series coefficients or find the Fourier series coefficients, you have to first make these checks because it may violate some of them, and if it violates one of these conditions, then you have to stop immediately and say that the Fourier series coefficients don't exist. You have to say, okay? So we will continue with other examples after the breaks. Let's give a break at this point of 15 minutes.